Snort.
I'm going to be telling you a little bit about Snort, what you can do with it, how it works, and then we're going to transition into a little bit deeper technical issues with how Snort has limitations right now, what's good about it, what's not so great about the 1.0 series, and then we're going to talk about Snort 2.0, the architecture of the system. So the first half of this talk is going to be more of a broad overview, and the second half is going to get into nitty-gritty of detection engines and strategies for doing all sorts of good stuff. Anyway, so I'm going to, I'll start my talk off by defining intrusion detection and see how many people jump up here and kill me. So what is intrusion detection? Well, it's the problem of identifying individuals who are using computer system without authorization. And probably you should pick up when people are attempting to break in, as well as when they are when they have broken in. Intrusion detection is not intrusion prevention. I get the question all the time, I want Snort to reconfigure my firewall. I want Snort to do active session sniping. I want Snort to basically give the attacker the ability to modify the configuration of my network in any way that he pleases. You know, it's a nice thought. I don't approve of it in general. I usually point people towards Perl scripts and Swatch when they want to do those sorts of things. Just because you pick up the attack doesn't mean you should necessarily have your automated system, which can probably be spoofed without too much trouble, in an automated fashion, shutting off network connectivity to things like the root name servers and corporate mail server, NFS servers, whatever. So intrusion detection is an extension of a site's policy, right? Okay, here's the really boring part. Without a policy, intrusion detection is just kind of, you know, this makes me feel bad, as opposed to, you know, we have specifically defined events and notification procedures, response coordination, those sorts of things. Having a policy defines what is not allowed. It defines what you're defending against, what you do when you discover an event, how you respond to those events, all those sorts of things. Without an effective policy, intrusion detection just generates a lot of noise and makes your admins upset. So I highly recommend, if you're going to use an IDS, you should probably put some sort of security policy in place. Now, having said that, if you're going to do IDS, you might want to take a look at Snort. So what is Snort? Where does the name Snort come from? I'll tell you that in a second too. Snort's a multi-mode packet analysis tool. Snort can be a sniffer, a packet logger, it can be a forensic packet analysis tool, and it can be a network intrusion detection system. It's a floor wax and a mouthwash. It does pretty much anything you could want to do with packets, you can pretty much do on the packet analysis side of the world. You can pretty much do with Snort. Maybe you have to tweak it, maybe not. Maybe it does it right out of the box, exactly what you want. But there are a lot of things that you could do with Snort once you have access to a network, and if you're running IP, of course. Where did Snort come from? Why did I write this thing? Basically, about 2.5 years ago, I was working for a large telco, and I was writing a honeypot system. It was a honeypot that would simulate an entire heterogeneous Class C network and software, and the government was using it. They were putting it in their Class B address spaces, and you'd have this random Class C out there with a bunch of vulnerable machines on it that looked like somebody had forgotten to put up the firewall. So I was writing this thing, and it was simulating all of these services on the network, and it was kind of cool. But the problem I was having is I was using TCP dump to debug the network traffic coming out of the systems. And one day I finally got upset enough with TCP dump that I said, well, I need a better sniffer. And so over the course of a weekend, I wrote Snort. And originally, that's all it was a sniffer. And the name Snort, basically, when I first wrote it, it was just a tool for me. I had to call it something. A.out was, I have too many of those on my system already. So I had to give it a name. It wasn't going to be main. TCP star had been taken, right? TCP dump, TCP slice. So I said, well, it's a sniffer. We'll call it Snort. Why not, right? Nobody's ever going to see it, so what does it matter? So I released it open source a month later, and turns out a few people saw it, and now I get the question all the time, is that an acronym? Did you really, what's behind that name? It's a mistake. But, it sticks in everybody's mind, so it's not that bad. So Snort metrics. Snort is still pretty small. It's getting a little chunky now. 800K source code download. We just released Snort 1.8 this past Monday night around midnight, and the source code tarball is now about 800K with all the tools that we package in with it. So Snort's still pretty small. It's portable. Snort runs currently on about 25 platforms. So if you have something that will compile libpcap, you probably have something that Snort can run on. Runs on Linux, runs on Windows, Mac OS X, all your various BSDs, Solaris, True64, all those guys. So Snort's an extremely portable piece of software. Snort's fast. Fast is hard to define, though. So I define fast as having a high probability of detection on a saturated 100 megabit network. If you have an event on that network, there's a good chance Snort's going to pick it up. We're going to talk about speed a little bit later, but for now we'll just say it's fast. Snort's very configurable. It's got an extremely easy rules language. The rules language is getting a lot more robust now, but the rules themselves are still pretty easy to write. It's got a lot of reporting and logging options. If there's a format that you want Snort to write data in, it probably already has a plugin built up to output to the format that you want. And best of all, Snort is free. It's GPL, it's open source, so it's free like free beer and free like free speech. That's probably one of the best things about Snort. There we go. So the design of Snort, we're going to talk more about this later, but for right now we'll just say Snort's a packet sniffing, a lightweight network intrusion detection system. I get a lot of crap about calling it a lightweight network IDS. The lightweight came from back in June of '99. I got a message from the guys over at Usenix. They asked me to write a paper about Snort and compare it to other IDSs. And at the time, Snort was pretty lightweight from a capability standpoint. It didn't support things like IP defragmentation and stream reassembly, any of those sorts of things. But it could sniff the packets. It could do pattern analysis. It had a decent rules language at the time. So I said, well, compared to the other IDSs that I was able to get my hands on at the time, Snort was pretty lightweight. So we called it lightweight from a capability standpoint at that time, but it was also lightweight from a footprint standpoint. It didn't suck up a lot of CPU, didn't take up all the RAM on your system. You didn't need to dedicate a box to just running Snort. Nowadays, Snort is much less lightweight from a capability standpoint. Snort can do all the things that you expect an IDS to do. As of 1.8, we just added stateful inspection to the TCP stream reassembler. So all TCP streams have stateful inspection by default, and the thing is optimized to be able to do up to 64,000 simultaneous TCP sessions. That was my goal when I was writing it. So from a capability standpoint now, Snort is less than lightweight, but from a system footprint standpoint, it can still be very lightweight. It's very tunable. Snort uses a libpcap-based sniffing interface. libpcap is the reason that we're so portable. Without libpcap, we wouldn't be able to run on all these platforms. libpcap allows us to sniff on pretty much any platform without having to know how that platform's sniffing interface works in particular. Snort uses a rules-based detection engine, signature-based. Signature-based detection gets a bad rap in the industry, but it's very effective, I think, for the vast majority of detection scenarios. And Snort's got a plugin system. We can extend the functionality with this plugin system. We can drop in preprocessors, detection plugins, and output plugins. So this allows us to shape the packet stream coming into Snort, extensively define detection scenarios, and then shape the output of Snort so that you can talk to databases, XML, whatever format you want, without having to rewrite the entire system. So in the detection engine, we have these rules and they form signatures. Now, signature-based detection gets a bad rap. A lot of the commercial people are really talking up their 7-layer stateful inspection of all the layers of the packets and application decoding and doing all of these other things. From a capability standpoint, that's a very nice thing to do. From a footprint standpoint, if you're going to do that, you get into the situation where you start eating the entire CPU of the system just to verify HTTP traffic, just to verify mail traffic and that sort of stuff. The capability to add that sort of functionality exists within Snort, especially now that we have the stateful inspection engine and all those sorts of things. But for the most part, the signature-based engine allows us to watch for things that we find hostile and lets you know when it sees them. The original intent of the detection engine in Snort was to be able to define things to look for and let you know when it sees them. So when I first designed the engine, it really it wasn't required to be stateful. We wanted to define packets that we wanted to see on the network and have the detection engine let us know when it saw them. So we didn't have this real need for, you must understand SMTP and tell me when you see a whiz login, or you must understand DNS and look for DNS buffer overflows or bad DNS traffic and those sorts of things. We were in the mindset of, I don't like this. When I see this on my network, let me know. And it's been a pretty effective detection strategy for us so far. Snort has a wide range of detection capabilities. You can pick up stealth scans, OS fingerprinting, buffer overflows, backdoors, CGI exploits, you name it. If there's packets on the wire, you can probably pick it up with Snort, unless it's encrypted. But that's the weakness of all network IDS. With the advent of the new stateful inspection system, we can do some other kind of interesting things. We do, I can pick up Nmap statefully now. Nmap OS fingerprinting, we don't just do packet-based pickups anymore. We actually run it through a state machine and say, that's somebody using Nmap to try to fingerprint our IP stack. We can pick up ECN traffic, explicit congestion notification traffic. There was a lot of problems when Linux 2.4 kernel came out, because people were turning on this ECN kernel option that would use the reserve bits of the TCP flags field, and it was setting Snort off because we were watching for queso scans with people doing the same thing. Queso set the reserve bits on the TCP flags. So now we can pick up ECN traffic. We can actually flag it explicitly as ECN traffic so Snort doesn't get confused, and the rules can be written to say, look for ECN traffic. If you don't see ECN traffic and you do see these other conditions, then it's probably a queso scan. Rule systems, flexible. Creation of new rules is very easy. Snort uses just a single line per rule, essentially, text file. So this allows people to pretty much whip rules out pretty quick. As you need them, as new events come out, you can write a new rule for Snort. I usually can write them, depending on how in-depth the analysis has to be, in anywhere from 5 to 20 minutes. Okay, so Snort uses these plugins. We have 3 different types of plugins in the Snort 1.x system. We have preprocessors, detection plugins, and output plugins. Preprocessors are run once per packet, and they allow us to do things like normalize traffic that we see on the wire and do stateful analysis and state tracking and state keeping, things like IP defragmentation, all that sort of stuff. So we do things like port scan detection, stream reassembly, IP defrag, all that's done in preprocessor land. We can rebuild packets out of the preprocessors and drop them into the detection engine. We can also do things like normalization. So if somebody sends you funky URL encodings, or if they send you funky telnet traffic or FTP traffic with embedded telnet negotiation codes, which is perfectly valid but breaks pattern matching. We can normalize the traffic to strip that stuff out and turn everything from whatever garbage format people are sending you back into normal ASCII so that the pattern matcher can actually access that data in the payload. And then we have the output plugins, which allow us to talk to whatever kind of output format we want. The detection plugins are very, very small plugins. They pick up or test one particular aspect of a packet per packet, and they can potentially be called many times per packet, because the Snort detection engine will say, I want to check the TCP flags for SYN. I want to check the TCP flags for FINAC. I want to check it for SYNFIN. So potentially a detection plugin could be called many, many times per packet. So the detection plugins are traditionally very small. except for the pattern matcher. The pattern matcher that we use to actually analyze the payloads of the packets for content, that's a pretty heavy-duty process, and it turns out that that's actually about the most time-consuming process that Snort does when it's running. So what can you do with Snort? Well, you can use it as a standard packet sniffing network IDS. You can do policy enforcement with it. If you decide that you absolutely must have your intrusion detection system, snipe sessions, and reconfigure your firewall, you can do that with Snort. Well, not reconfigure your firewall. I absolutely refuse to put that functionality into Snort directly. But you can have Snort do active session sniping. There's also there's kind of a movement underway to make Snort be able to do a new trick called gateway IDS, or packet scrubbing, where the net filter interface or the divert sockets interface on BSD or Linux can hand the packets up to Snort from the firewall. Snort can disposition those packets, as we say, disposition them and say, good packet, bad packet, drop this packet, drop this session. So you can actually have Snort, instead of being a passive monitor on the side, be an active participant in allowing traffic through or not. And doing that gives us some advantages, and I'll talk about that in a bit. Using Snort as a honeypot monitor, this is actually one of the first tasks Snort was put to. I wrote this honeypot, and it was for use by the government, and I discovered, much to my horror, when we deployed it, that, hey, not all these government admins are security experts. They can't look at these exploits raw as they come in and just figure out what they are. What's up with that? And so that's where the Snort detection engine actually came from. We wanted to be able to start classifying things for the users, so that we could demo. Since I had this tool, it was kind of becoming like a Swiss Army knife. It was having all these uses. So since I already had this tool to do the packet analysis and classification, I kind of showed that to the government and said, you know, more like this, and they said, oh yeah. So one of the first uses of Snort was actually as a honeypot monitor. And you can also use Snort for scan detection and traps. If you don't have the money for a honeypot, or you don't have a spare Linux box laying around, you can set Snort up to play your home field advantage. You know what services and ports are open on your firewall and in your network. You can set Snort up to watch for things that should never be there. If you don't allow rlogin on your network, you should never see rlogin traffic. Define a rule that says, I saw rlogin traffic. Once you know what the home field advantage is, once you know what your home field looks like, it's much easier to look for things that are abnormal, like traffic going to ports that you don't have open on any systems. Or, now that we have stateful inspection, we can look for completion of three-way handshakes on ports that should never be open. So this is kind of interesting. Well, that port should never be open, but I clearly saw it connect. There was data exchanged bidirectionally, and that's bad. So we can set up those sorts of things using Snort as well. Okay, so if you're going to put Snort on your network, where does it go? Well, right now the two bottom ones here, the statistical IDS and network IDS, Snort can do those in the 1.x series. Snort 2.0, we're hoping, if the design comes off the way it's supposed to, we're going to be able to do host-based intrusion detection with it. I'm going to talk more about that, but in Snort 2.0, we're thinking that we're going to be able to turn it into a host-based IDS as well as a network-based IDS. Snort 2.0 is also going to have this gateway IDS mode, so you can put Snort on the firewall directly and have it do active intrusion detection, where it shuts down sessions in real time as they come through, drops packets, snipes sessions, does whatever you want. So when you're using Snort, you see our nice Swiss Army knife there, you have your three main operational modes plus your forensic packet analysis mode. Your operational modes are configured through the command line. I'm finding that people are having a lot of trouble lately with the Snort command line. I think there's something like 30 command line switches that we have available. It's kind of unfortunate because people are sending me these kind of crazy configurations that they're setting up now. There's a file that comes with Snort called usage. If you're going to use Snort, I recommend you read that file. For the love of God, read that file. If you don't read that file and you send me email for something that's in that file, I turn into Theo. It's an amazing metamorphosis. Anyway, one of the new features in Snort 1.8 is if you If you don't give it any command line options, it automatically tries to go into network IDS mode. It looks for the snort configuration file, the snort.conf file in the etc directory, and it also looks for it in the local directory. And if it finds it, it will fire itself up into IDS mode. One of the things that's not documented at all in the, I don't think, did you document the new config options? I don't think I told you about them. No. This guy right here is Chris Green. He wrote the PDF that ships with Snort 1.8. He's a good man because he saved me from having to write all that documentation. Anyway, there's config options that you can do in Snort to replace all the command line switches now. So you can build a configuration file that has Snort running right out of the snort.conf without having to give it any command line switches. So the nice thing about that is you drop the snort.conf into your etc directory, you give it all the config directives in the snort.conf file, and it fires itself up. You can just start it automatically. So in sniffer mode, Snort works a lot like TCP dump. It decodes the packets and dumps them to the screen, right? It's got a BPF filtering interface exactly like TCP dump, so you can shape your traffic that comes in. People don't use this feature enough when they have things that they want to filter out or things that they want to filter explicitly for. It's not widely advertised that the BPF interface is in there, but it's really useful for doing things, especially if you want to shape analysis on your network when you're doing something like you're doing exploit analysis, or if you are telnetted into a box, or worse yet, SSH'd into a box and you don't want to see your SSH traffic. Use the BPF filtering interface, because otherwise if you SSH into a box and then start Snort on that box, as SSH updates the screen with the packet dumps, it's going to send traffic back to you, which in turn is going to cause more packets to come up on the screen, and eventually you lose your SSH terminal because it gets into this pretty nasty loop that you can't really break out of. So use the BPF filtering interface. It's well worth it. So what do the packet dumps look like, right? Okay, so I wrote this whole thing to replace TCP dump because I was sick of looking at just straight up bytecode dumps. So here you see a couple of Snort packets. These are from a telnet session. You can see some of the features here. You get your IP and port layout on the top line, and then it's decoded by layer. So the next line is always IP, the next line is always TCP or UDP or ICMP. We decode by layer in Snort and display by layer in Snort so that things are deterministic. They're always in the same place, so it's easy to write additional logic for Snort, like Perl modules. There's some Perl modules out there that can analyze a Snort packet dump file in straight ASCII and actually do reverse fingerprinting on the, or not reverse, passive fingerprinting or identification of the participants in a session by looking at the raw packet dumps. The other nice thing about Snort is this decoded application layer at the bottom. You can see this is telnet negotiation going on here. See all the FFFCs and stuff. You've got the raw bytecodes on the left, and then you've got the ASCII on the right. For me, that was the whole reason of writing Snort originally, was to have that decoded ASCII on the right, because the trigger event that kicked off Snort was I was writing this honeypot, and one of the RPC simulators I had written was actually transmitting its usage line. You know how when you type a Unix command with no or wrong options, it'll dump its usage on the screen. Well, it was dumping its usage to the network, and I was looking at the output, and I'm like, well, that's all in the ASCII range. What's going on here? So I got my ASCII chart, and I started translating it. And I saw it was a usage file, and I said, well, that took 10 minutes. I could have done that a lot faster if my sniffer actually printed out the ASCII and the packets instead of making me decode it myself. So that's why I originally wrote Snort. So how's it different from TCP dump? Well, you know, there you go. That's a TCP dump right there of two similar packets in a telnet session. And you can see that that's not nearly as much fun to look at. Plus, it doesn't have the cool splits between the packets, which I think is probably the best feature in Snort. Okay, so a couple weeks after writing Snort, I said to myself, gee, sure would be nice if I could save those packets to the disk and examine them later. Be really nice for watching my cable modem. I'll turn my cable modem on when I'll turn Snort on when I go to work and have it log all the incoming traffic, and I'll look at the packet dumps when I get back. So thus begat packet logger mode. We have now since you can use a configuration file, we can put Snort into packet logging mode using the database. We can also output to XML, and you can go and use flat ASCII and TCP dump output options also. Some people, this is kind of the shadow model. You log all the data on the network, and then you post-process analyze it for hostile activity. Packet logger mode allows that. I mostly use the packet logging mode actually when I'm doing signature development. I run an exploit on a network, I save all the packets, and then I analyze them after the fact to look for the exploit and figure out signatures for it. Then we get into network IDS mode. Network IDS mode uses all the things that Snort can do to do signature-based analysis, and it also does anomaly detection to a degree. So we do port scan detection, we can do IPD fragmentation, stream reassembly, application layer analysis, normalization. We can do all sorts of cool things with Snort once we get into network IDS mode. And we have a lot of output options available too. We support currently in the database output, we support MySQL, Postgres, Oracle, Unix ODBC. Somebody has a MS SQL interface for the database plugin. Another guy is working on a Sybase extension for it. I think, are you in the room, Roman? Roman Danilou is the guy, one of the guys that does the work with ACID. I hope Danilou is the right way to pronounce your last name. Anyway, he's the guy that's responsible for the database output plugin and for ACID. It was a very welcome addition to Snort when it showed up. And Roman and Jed are also working on the XML output plugin and the SNML DTDs from certain Carnegie Mellon, right? Yeah, but they're the guys who maintain those output plugins. We also support TCP dump binary format. The TCP dump format is kind of this universal language of sniffers everywhere. Most sniffers can read and write TCP dump packet formats. So this allows us to transport Snort portably to other analysis interfaces. Allows us to archive things in formats that we'll be able to analyze with other tools years from now, things like that. We have a new unified format that I'm going to talk about later. The unified format is kind of the future of Snort output. I'm going to tell you more about it later, but suffice to say that it's a lot like the TCP dump mode, but there's a couple of different modes, and it's very fast. We also support ASCII, syslog. We can send Win pop-up messages if you want that. If you want to be clearing dialog boxes all day long. So Snort, being a signature-based system, must have signatures. As of last month, right at the beginning of the month, we had about 1,300 signatures. We've got a very broad set of signatures out there for people to use, and we have multiple detection modes that are available versus via these rules and plugins. We can do rules and signature-based analysis. There's a plugin in Snort, a preprocessor called SPADE that does, it's called the Statistical Packet Anomaly Detection Engine. SPADE does statistical intrusion detection, statistical anomaly detection using Snort. We can do protocol verification with preprocessors in a lot of cases where we actually analyze application protocols, things like that. All right, so now we're going to get to kind of part two of this talk. We're going to talk about Snort's architecture and how it works and how we're going to make it work better. So this is the data flow through Snort right now. We sniff packets off the wire. They go through the decoder, hit the preprocessor, then go into the detection engine, and if there is an event somewhere down this chain, it all goes out through the output stage. It's pretty decent architecture. It gets the job done. So the architecture of the current system grew. It wasn't planned, it grew. We've ripped out a lot of code and re-implemented a lot of code in Snort over the years, and basically taken it from being a sniffer to being a packet logger to being a network IDS and forensic analysis tool. So as we've built these things up, you can see that the maturity of the system kind of of the subsystem within Snort kind of defines how fast that subsystem is. I spent a lot of time writing packet decoders. The packet decoder in Snort is very, very fast. It's practically instantaneous. Snort basically sets a couple of pointers and checks a couple of lengths and then goes to the next layer of packet decoding. So we can decode packets at full 100 megabit speeds. Actually, we can decode packets. I haven't found the limit on how fast we can decode packets because we run into the limits of libpcap before we actually run into the limitations of the decoder. We don't drop any packets in the decoder. The detection engine is fast. We've done pretty much all we can to make it as fast as possible in the current architecture. Making it faster is going to require some rethinking of the way that we do things, and we're going to talk about that. But the detection engine for now is fast. We can actually do, depending on what rules load and things like that, we can actually detect and alert on 48,000 packets per second, full 100 megabit per second traffic. But what the problem with trying to do that is, in the last layer here, the output and preprocessor modules, the performance of those subsystems are extremely implementation dependent. I can get the Snort detection engine to alert on doing content checks, actually hitting the pattern matcher 48,000 times a second without losing a packet. If I turn off the logging options, I basically wire them to dev null. As soon as we turn on the logging, the performance takes somewhat of a hit. In binary logging mode, we can log roughly about 8,000 packets per second, which is entirely configuration dependent, depending on your hardware, what kind of disk you're using, which operating system, all those sorts of things. But a safe number is around 8,000 packets per second can be logged in the fastest logging modes that Snort has. So if we can alert on 48,000 things per second, but we can only log 8,000 things per second, that's kind of a limitation of the architecture. The Snort 1X detection engine is a three-dimensional linked list. The first and second dimensions, the first two dimensions, contain data nodes that store data that we want to compare against the current packet. The third dimension contains linked lists of function pointers to test those nodes against the current packet. So essentially, each node in the detection engine knows how to test itself against the current packet automatically. The entire engine is walked recursively, and it's turned out to be a very, very fast and robust way of doing packet analysis. It's kind of vengeance on my data structures and algorithms professor from college, really. I sometimes fantasize about sending him an email and saying, hey, have you checked out my three-dimensional recursively walked linked list system that does packet analysis in real time? Jerk. Who says I don't know anything about data structures? Oh, it was you. Anyway, so the detection engine currently uses a first exit detection strategy, and what first exit means is as soon as you detect something, pop out of the detection engine and let me know what you detected. So the concept behind that is, if we're going to log a packet, let's log the packet, let them know that something interesting happened, and get on with our lives. The people who are doing the analysis on the backside theoretically should be intelligent enough to look at that packet, and if there's anything else in there that's interesting, be able to figure it out themselves. Turns out that maybe wasn't the best way to do it, but it's certainly a very fast way to do it. We're working on ways to be able to do what we call last exit detection strategy in Snort 2.0, where Snort continues to go through the entire detection engine all the way to the end and alerts you on everything that's happened, everything that it detected for a packet. So in the detection engine, we load our rules in, and there's two parts to every rule in Snort. You have the rule header and you have the rule options. Rule header tells Snort, kind of defines what you're interested in from an IPs and ports and protocols standpoint, and what you want to do when you actually have an event go off. So you have your action. For this one, we have alert, and then the protocol, IPs, and ports. And then we have the rule options. And this is what we want to look at inside the packet to actually check for hostile activity. And Snort parses these rules and reads them in and turns them into a rule node. You'll notice that on all of these rules, the rule header is the same, the rule options are different. Snort optimizes that internally into this kind of structure where you have a rule node that heads a list, and then you have sets of what we call option nodes in an option chain. So all of those rule headers were the same, so we put them under one rule node. So Snort only has to do that check once, and then it walks down the list of option nodes that are in the system. So if we run into traffic that's TCP coming from 1.1.1.1 going to 2.2.2.2, then we're interested in checking this option chain, and we say, are the TCP flags set to SYN-FIN? If they are, then tell me it's a SYN-FIN scan. Are they SYN-1.2? Well, then maybe it's a queso scan. Is it just a straight FIN flag? Well, then it's a FIN scan. So Snort organizes these rules and does optimization internally so that we have a fast detection engine. And what it does is, as you load rules into the system, it parses these rule nodes and option nodes into this big two-dimensional linked list. And the third dimension kind of extends into the screen, and that's where all the function pointers are. So through this development process, we ended up with a very high-speed packet decoder and stateless IDS. I get the question a lot, how fast is it? How much hardware do I have to throw at this to watch network N? I don't know, really. It's entirely configuration dependent. If you're watching a network that just has web traffic on it at all, and you're going to load the entire set of detection rules, Snort's going to be hitting its web traffic preprocessors and rules constantly. So it's going to be hitting the pattern matcher constantly, and that's going to slow it down. So how fast is Snort? Well, it's configuration dependent, but if you pay attention to your configuration and you tune it carefully, Snort can really do about 100 megabits per second without really missing a beat. I've tested Snort up to about 320 megabits a second. At 320 megabits a second, Snort loses about 50% of the packets. But I discovered that most of the overhead, most of the reason it was losing those packets was not that Snort was too slow to handle it. It's that libpcap couldn't keep up with the packet stream. There was so much interrupt overhead on the system just getting the packets from the NIC to main memory that we were losing about 50% of the CPU just handling interrupt servicing at that speed. So Snort's pretty fast. Snort can probably do 150 to 180 megabits a second without breaking too much of a sweat if you really, really tune it carefully. But if you go home and it doesn't do it on yours, don't flame me, please. The flexibility of Snort really turned it into the platform of choice for R&D in a lot of government and university settings. I'm going to talk a little bit about a paper that came out of Los Alamos a few weeks ago that talked about pattern matching performance of Snort and improvements that we could make in the system. Spade was developed with DARPA money. The Spade plugin was developed by a company called Silicon Defense with money that they got from DARPA. There's also, I know the Navy's been playing around with adding some Snort plugins. I'm aware that the NSA has been playing around with adding Snort plugins. So if you want to do rapid development of some intrusion detection concept that you've come up with, Snort gives you an API that allows you to see a decoded packet stream in real time and do any sort of analysis and report in any sort of fashion that you're interested in. And so a lot of government and university people have really picked it up and started running with it. I think there's actually somebody at a university out there is doing FPGAs. They looked through the Snort stateful inspector and TCP stream reassembler, and they're actually looking at implementing it in hardware. So it's pretty interesting what people in research environments do with Snort when they get a chance. All right, so let's talk about Snort 1.x limitations now. So Snort is completely IP-centric. If you're not sending IP packets, Snort's not interested. More to the point, Snort doesn't even have the capability to really get outside of ARP and IP. Our packet analysis has some limitations. IPD fragmentation and stream reassembly are done as preprocessors. They should probably be done in the decoder phase, actually. They should be moved out of the preprocessor space because they're really an essential attribute of the decoding and packet analysis systems. The internal data structures don't really scale well for the addition of new protocols. We've got this one big structure in Snort called packet. And every time you want to add a new protocol to Snort, you have to add a new pointer in the packet structure to point to that protocol header. So that doesn't scale very well, because eventually this packet structure gets gigantic. I think it takes up like 2K memory right now just to instantiate one of these things. So that said, just because it doesn't scale very well doesn't mean that it's actually very hard to add new protocol support. I added 802.1q support to Snort in about 45 minutes. It's really knowing where to add things into Snort that's kind of the daunting thing. Since the packet analysis system doesn't have a well-defined plug-in API, a lot of people find it pretty daunting to add new protocol support to it, except for the guys who've been there since day one, like myself and Fyodor Yerochkin, guys who actually had a hand in developing it from the first place. And another packet analysis kind of limitation we have, we don't really decode the application layer. We let the detection engine handle doing analysis in the packet payloads. So this can be somewhat of a limitation. Okay, we don't decode DNS, right? So there's some DNS things that are kind of hard for us to pick up. We don't decode HTTP explicitly, so there's some things that can get by us theoretically, or we have to do more work really to analyze HTTP traffic. Those are the sorts of things that it'd be nice if the packet engine, the packet analysis engine, could do that stuff. So the detection engine and preprocessors, what are the limitations in these systems? Well, it turns out I've discovered one of the blessings of having an extensible plug-in system is that all these people can add all this functionality to Snort in a relatively painless manner. But it turns out I didn't really think about the second-order effects of doing that when I first wrote the APIs, because turns out not everybody's concerned with performance like I am. I mean, people are concerned with performance generally. They don't want to see the system come to its knees. But there's some better plugins in Snort than others. Let's put it that way. Not all preprocessors are created equal. There's a lot of code in Snort that sometimes I have to scratch my head about, and well, there's not a lot of code in there. There's a lot of code in there that could probably be written faster, especially in the preprocessor and output world. Adding additional protocol support to the detection engine is not well modularized. Now, this is somewhat of a limitation. You can't just drop another protocol into the detection engine seamlessly. Turns out I added the IP protocol to the detection engine for 1.8, and it only took really 7 lines of code to do it, but the 7 lines of code that had to be added to the system to actually use IP as a protocol that the detection engine could understand and you could write rules against, that was spread over about 7,000 lines of code in 5 files. So knowing which 7 lines to add and where to add them pretty much took me to do it. So that could probably be better. The rules description language is somewhat limited at the protocol level. It's easy for us to describe things like IP and TCP, UDP, ICMP, well-defined protocols. Once we get to the application layer, once we hit NetBIOS and web stuff, RPC, SMTP, those are protocols that can get pretty slippery because they're that's where the applications are running. So this is stuff that's is hard to add as another rules option to the detection language. In the output space, some of the output plugins are slower than others. That's not so hot. The variable output format means that performance is extremely variable based on your selected output modes. And given that, there's no way to control Snort's performance effectively from an author's standpoint, right? I can't dictate how Snort is going to perform in its output stage. So I get these, I get bad reviews sometimes from websites and things like that. Well, nice detection engine, but it's a little slow on the output side. And I get a lot of email that says Snort is eating 90% of my CPU. What's going on? I say, well, are you using MySQL? Yes. Well, there's your problem. The problem is that some of the pieces of Snort, even though they're written pretty well, such as the detection or the database output system, even though they're written pretty well, you still have to wait for that database. You still have to do inserts and selects and things like that. So you're waiting on the database. So when the database plugins are turned on, or the XML plugins or the CSV plugins, all the output plugins that we have, depending on which output plugin you select, you really can get into trouble from how much the CPU it uses and how fast it's capable of logging. But we're going to fix that too. So in Snort 2.0, the architecture of the system, the basic goal is better, stronger, faster, right? We want to be faster. We want to be more extensible. We want to be faster so we can do things like support gigabit analysis. Now, supporting gigabit is one thing, but actually being able to get the hardware that's fast enough to read in gigabit traffic is another. I think that for true wire speed gigabit type stuff, we're going to end up with having to do hardware accelerated intrusion detection. That's kind of beyond the purview of us people who write our code from 11 o'clock at night till 3 in the morning and don't get any money for it. So we're going to try to make Snort as fast as we possibly can as a software system. We're going to make it more extensible. There's going to be more places for plugins. It's going to have better protocol support. We're going to be able to support protocols that it currently is a real hassle to look at. And I use my 25-cent word here. We're going to be better able to analyze the full gestalt of network intrusion activity, right? We want to be able to analyze all aspects of network intrusion activity. We'd like to be able to analyze things like host-based intrusion activity as well. So we're going to see if we can write Snort 2.0 to do those sorts of things. So in 2.0, we're going to have more plugins, right? We're going to have data acquisition plugins, traffic decoders, so you can drop in arbitrary protocol support. We'll be able to add in things like full protocol verification and analysis, multipath traffic flows for packet and stream reassembly. I don't know if we necessarily want to add this one. Is Tim Newsham in the room? No? Good. He wrote the paper on defeating intrusion detection using TCP stream reassembly variations and IP fragmentation variations. We're going to make Snort able to consider the traffic in multiple ways. Different operating systems put IP fragments together differently. So this can be exploited since a standard intrusion detection system has to kind of pick one way and go with it. We're going to see if we can multipath the data streams through Snort so that we can do things like intrusion detection on IP fragments for all types of operating systems instead of just one set of operating systems. At the same time, these multipath traffic flows that we're talking about, this means we're going to have two paths for the data to go through Snort. We're going to have a packet path. We're going to have a stream path, the application path. So this will allow us to do things like put together application layer streams and analyze those explicitly instead of having to analyze them on a per packet basis and do funky things like our TCP stream reassembler right now, the way it puts packets, the way it puts streams together so that we can analyze these streams statefully. It actually builds fake packets from the TCP streams and runs them through the detection engine. So we're going to make it so that the streams are explicitly on their own data path through the system. This will allow us to do some interesting things in the pattern matching space as well. We're going to have multi-format rules input plugins. So if you want to read your rules configuration language in from something other than the flat text file we're using right now, like a database, or if you want to do your rules input system in XML, you'll be able to drop in an XML rules reading plugin that will be able to load these off the disk in whatever format you want. And then we're going to have pluggable detection engines. Right now, the detection engine in Snort is kind of like a really big preprocessor in the current architecture. But what we're going to do in 2.0 is we're going to talk about being able to add alternate detection strategies into Snort. We're going to be able to do things like standard, regular network IDS, target-based IDS, where you marry the IDS with a scanner like Nmap, statistical intrusion detection, host-based intrusion detection, gateway intrusion detection. You'll be able to drop these analysis engines into Snort as modularly as you can drop regular plugins into Snort right now. So if you have some cool new detection strategy that you want to try out, you can actually drop that right into Snort. So one of the big improvements that we're kind of aiming for in 2.0 is to improve the pattern matchers. Right now, Snort uses what's called a Bohr-Moore algorithm. It's about the fastest pattern matching algorithm available for doing straight-up pattern matching. The problem is that we have to call it many, many times per packet potentially to be able to analyze the payloads of packets. For instance, say we have some CGI content that we want to look for. So we call this Bohr-Moore routine. We have like 300 CGI checks that we do. So we call this Bohr-Moore routine 300 times per packet. So that's a little inefficient. The guys at Silicon Defense came up with, they did a paper on re-implementing the pattern matcher using what's called an Aho-Korsic routine. So what this does is it allows us to take all of the content checks in a chain, in an option chain. So basically, right here, these option nodes we turn into option chains essentially. See how they all go vertically and the arrows point down, so that means they're a chain. So what we're going to do is with the Aho-Korsic routine, we're going to take all the content checks for a given chain and we're going to put them into this big what's called a trie. And what this allows us to do is it allows us to check all the patterns in one shot. We call the pattern matcher once. The performance gain from that is about, I think it was, on their test implementation, it was 38% faster than the existing system. Paper came out last month from guys at Los Alamos using what's called a setwise Bohr-Moore horse pull algorithm. No giggling. So what this algorithm does for us is it's got a faster way of doing it, but there's a little bit of overhead cost right up at the beginning of it. So the guys at Los Alamos figured out that if we select the pattern matcher based on the number of checks that we're doing, the amount of content checks we're doing in a rules chain, we can optimize based on how many checks we're doing. So for 3 or less checks, we should use the standard Bohr-Moore. For up to 100, we should use the standard the Aho-Korsic routine. And over 100 pattern checks in a single option chain, we should use this Bohr-Moore horse pull algorithm. And they tested it out, and they saw a 500% increase in the pattern matching performance of Snort. So we're going to put that one in, definitely. The output stage of Snort, we're going to turn it into a spooling output stage. We're going to go with a single output format for Snort and move the output plugins into another tool called Barnyard that I'm currently working on. I'm really not good at naming things at all, am I? So we got this thing called Barnyard that's going to sit there and post-process these spool files as they come out of Snort and reformat the data for whatever final output format you want. So what this allows us to do is it moves the performance hit for doing things like database writes out of Snort and to an external program that's running in an entirely another process. So we don't have to worry about things like well, you know, you're using the world's slowest database, so you can only log 100 events per second or something like that. And this will allow us to do deterministic performance measurements of Snort. And focus performance improvement in the detection engine, the decoder, and the output stage. We can actually sit there and say, well, Snort only outputs one format now. Let's make that format as fast as possible. So here's the new system, the Snort and Barnyard integration. By the way, these new Snort logos. This is this logo and the one on the front page there from Ty Samaka. He's the guy that does the artwork for OpenBSD, and I asked him to do us up some new logos for Snort. So I've been pretty happy with these logos. They're better than the old pig, the old nose-on pig, definitely. Anyway, so So Snort takes the traffic in off the network, and then it logs to these unified spool files. You have your unified alert spool and your unified log spool in the current implementation. Then Barnyard reads those spools, and it has its own output plugins. Basically, the output plugins are moved out of Snort and they're put into Barnyard, and then Barnyard has its final output format or formats, so it can send the logged packets off to a database or XML or whatever you want. So that's kind of that's the future of Snort's output stage, and this is pretty much implemented in the current 1.8 code. We can generate these unified alert spools. These spools are in our pure binary format. We don't do any data manipulation to speak of, so the output is very, very fast. On a fast disk, on a fast piece of hardware, you should be able to do at least 10,000 events per second out to the disk with this unified spooling stage. And if you want to experiment with it, you can actually experiment with it now. I'm hoping to get Barnyard out soon. I mean, I've got to, because we got this baby on the way, right? I'm hoping to get Barnyard out probably in the next couple of weeks. Once Barnyard comes out, you're going to see this this architecture actually be realized. So the Snort 2.0 detection engine, it's going to self-optimize a lot more than 1.0 or 1.x. The rules will be treed to a greater extent. See, we have this tree. And most tests are only going to be performed once. So right now we get into a situation where we check the TCP flags constantly to see if a connection has been established before we do a pattern match. Well, if you've got 300 rules doing 300 flags checks for the same flag, that's probably not efficient as it could be. So that's the way Snort does it right now. And what we're going to do in the 2.0 detection engine is we're going to tree this out a lot more. So the detection system acts like a funnel. So it funnels down to the final detection things that we want to look for. So when we do this, we'll be able to load more rules with less impact on the performance of the software. Snort can right now load probably, I've heard of people running ridiculous numbers of rules in Snort. I've heard of people running tens of thousands of rules in Snort, and they say it does an okay job on slow networks. But right now the practical limit, if you're going to be doing 100 megabit and up, you're probably looking at about 1,000 rules loaded max at any given time. With this system, we should be able to do a lot better than that. The construction of this engine is going to allow us to do a last exit detection strategy. Because we're going to be so much faster than the existing system, we can spend more time in there and do more detection work. So we're going to put an option into Snort 2.0 to select the exit strategy from the detection engine, where you'll be able to say, pop out as soon as you hit an alert event, or show me all of the alert events. So here's the current detection engine. You have your action type chain or your action type tree. Then you have your protocol tree, and then you have your rule header and your rule options. So as you can see in the rule options field here, we're doing 3 content checks, and we check the flags in each one of them for ACK plus, ACK and any other flag being up, to see if this session is up and running yet. So what we're going to do in 2.0 is this. We're going to chain down through the system a lot more. So you can see here we're only doing 1 ACK check at the end of it, and then we've got our content matches. And our content matches will be chained off the Boeremore horse pool and the Aho Corsic routines as well. So this is going to allow us to focus down, filter down, funnel down to the things that this rule can actually fire on, or this packet can actually cause to fire a lot faster. So it'll allow us to go much faster. We're also going to add acquisition plugins. As I've been describing, libpcap is pretty much a big performance bottleneck. It allows us to be cross-platform, but it's a blessing and a curse. We're cross-platform, but we really have a tough time getting over about 150 megabits a second, depending on your hardware. The acquisition plugins allow arbitrary data input sources. So what this does for us is it allows us to do things like develop high-speed packet acquisition interfaces. So we can talk directly to the NIC driver on a specific operating system if we can write an acquisition plugin for it. So in the general case, Snort will still support libpcap. But in the specific case, if you have some piece of hardware that you want to optimize Snort performance for, you'll be able to write a plugin that can talk to that platform's packet acquisition interface, its network card, a lot faster than libpcap can. And this allows us to do some kind of cool stuff. Once we have these acquisition plugins, we can make Snort talk to net filter and divert sockets, this new PF interface in OpenBSD. We can do gateway IDS. Since we're doing this multipath data through the Snort engine now, we should theoretically be able to do host-based intrusion detection. For instance, write an acquisition plugin that only takes in stream data and only pushes data down the stream path through Snort, and hook it up to your log files, or hook it up to a system call watcher. So watch for system calls, watch for people elevating their privileges when they shouldn't be able to do that, stuff like that. Theoretically, the combination of acquisition plugins and this new stream data path through Snort will allow us to do host-based intrusion detection. Gateway intrusion detection, this is something that's available right now, actually, in a couple of implementations. If you're active in the Snort users community, or if you're just on the Snort users mailing list, there was an announcement on Monday. There's a new company out there that's produced an open source gateway IDS based on Snort using net filter in Linux. So we'll also be able to do decoder plugins. This gives us arbitrary protocol support in Snort. Snort is currently limited to Ethernet, FDDI, Token Ring, all of these protocols you see here. It's hard to write new protocols into Snort right now, relatively difficult. Once we have these plugins, we'll be able to drop arbitrary protocol support into Snort. But the downside of doing that is that we're going to have to modify the detection engine to be able to handle these protocols that it doesn't necessarily know about. And that's going to be somewhat of a challenge to do that. But I think that it'll be really nice if you can write up a decoder plugin for Snort, drop it in the system, and Snort can automatically recognize that protocol, decode it, and do intrusion detection on it. So we're going to make a big effort to be able to add modular decoder support into Snort 2.0. And we're also going to develop these pluggable detection engines. Just because we do signature-based IDS doesn't mean you have to do signature-based IDS. So we would like to take the IDS engine and actually make that pluggable as well. And this lets us do some interesting things. You can do Snort plus net filter or divert sockets to do a packet scrubber. Snort plus nmap to do a target-based intrusion detection system where you scan the network. It tells you all the ports that are open on the network, and also tells you the operating systems, and lets you configure the entire detection engine based on the targets on the network. Kind of a joke. You can do Snort plus SAS and do a statistical anomaly intrusion detection, but I understand that SAS actually has, they're kind of half joking about it still, but they actually have some sort of functionality that can actually do statistical anomaly detection when hooked up to an intrusion detection database. So it was a joke, but now it turns out that it's actually something they're producing. These two top ones here are very interesting concepts in intrusion detection. We can do some pretty neat things once we go into target-based or gateway-based IDS mode. When you have a gateway IDS, intrusion detection systems traditionally have problems with evasion at the TCP and IP levels. So, and where the problem is that different operating systems implement their IP stacks differently, and their IP stacks are rarely RFC compliant. So intrusion detection systems try to catch everything that's coming by on the network, and they try to interpret it, hopefully in terms of the same way that the target is going to interpret it. Well, with a gateway IDS, we can do some kind of cool stuff. Once the intrusion detection system is hooked up to this hooked up to the firewall, once the intrusion detection system becomes a a gateway device, instead of being a passive listener on the side, the intrusion detection system can say, this is the way that we do IP fragmentation on this network. If you don't conform to that, your packets don't come in. This is the way that we do TCP streams. If you don't conform to that, your packets don't come in. It turns the IDS into kind of the firewall Nazi. The IDS sits there and says, you know, thou shalt not pass. And that's it. So you either have to have packets coming in properly or not at all. So this allows us to get around a lot of the evasion scenarios. We can detect when people are doing funky things with their IP fragments and TCP streams pretty easily. Doing something about it is really hard in a passive mode. But in an active gateway mode, we can define what proper behavior is, and then we can say, this is how they're going to look. If they don't look this way, they don't get in. And that gets rid of the whole evasion problem. Target-based intrusion detection is kind of the same thing. Target-based intrusion detection, we go out, we scan the network for ports that are open and vulnerabilities and operating systems. Once we get the information back from a system like Nmap, once we get the information on what OSs are out there, we can configure the detection engine in real time to do IP defragmentation in terms of the targets on the network. We can configure the engine in real time to do TCP stream reassembly the same way. We can also tell the engine that this guy is an NT host and he's running IIS, so don't do any Apache checks. And don't false alarm on any Apache checks. And if you see any Unix things come in, don't alert on them because he's an NT box. This guy is a Solaris 2.6 box. He's vulnerable to everything. So target-based IDS actually gives us a lot of flexibility and a lot of power to look at the network in terms of what the network is vulnerable to and to analyze the traffic how in the same way that the targets on the network see the traffic. So between gateway IDS and target-based IDS, you can really do a pretty nice job of covering your network. There is some work going on in both of these right now. I just told you about the gateway IDS. Nessus has a new mode where it will spit out snort rules based on what it detects on the network itself. So it goes out and scans the network and then generates a snort configuration file based on what it sees. That's pretty cool. Target-based intrusion detection, doing something like snort plus Nmap, would take some coding, but it's very doable, especially once you have pluggable detection engines. Okay, so learning more. Go to snort.org. That's the place for Snort. Read the documentation. I think I already said that, but read the documentation. Read the FAQ, read the usage file, README file, and man page. A lot of the usage file is actually integrated in with the writing snort rules documentation now. So if you go to that URL for writing snort rules, you'll also see the usage doc there immediately. We have some books if you want to learn more. Stephen Northcutt does some good books on intrusion detection. Paul Proctor did a nice one, the Practical Intrusion Detection Handbook. I thought that was a pretty decent book for getting up to speed. So we're kind of at the end here. There's my email address. You can get Snort from snort.org. The Win32 version is maintained by a guy named Mike Davis. He's at datanerds.net. You can get snort rules from whitehats.com, the Arachnids database. You can also get snort rules from snort.org. Silicon Defense has commercial technical support for the open source Snort platform now. So if you are running open source sensors on your network and you need some support, they actually are doing support contracts now. If you need to kind of take the next step with Snort, you should give my company a call, sourcefire.com, or Sourcefire Incorporated. We just started up recently, and we're producing commercial Snort network appliances, network security appliances. So basically, if you've got a Snort implementation and you need to take it to the next level, Sourcefire is probably a good place to check out. Security information, you guys know all the sites. So that's about it for me. You guys have some questions? There's got to be some questions.
You said that Barnyard should be out in a few weeks. Did I also understand you to say that we don't need to wait until
Right. Yeah. The 2.0 stuff. The question is, Barnyard's going to be out in a couple of weeks, so we can start using that as soon as it is. Yes, that's totally right. Other questions?
How does Snort scale processes? Is it able to handle all this?
Yeah. The question is, how does Snort scale across multiple Question is, how does Snort scale across multiple processors and multiple NICs? It doesn't. Snort is a uniprocessor kind of system. Since we're open source, most of the guys don't have a whole lot of CPU power laying around. So right now, it doesn't use threading at all. There's some effort to actually develop that stuff, but most of the time, you just fire off multiple Snort instantiations for each network card. Under Linux, you can specify the all interface, and you'll see all the interfaces simultaneously. And Linux, in multiprocessing will get you some speed advantages just from libc being multi-threaded and stuff like that, but it's not going to be a huge performance gain. Yeah, you'd be better off if you put one processor on each network. Yep.
In the same vein, you said you're going to switch. It sounded like when it's 3 apart or 2. Do you think that you might have split those on a multiple processor? So one part can run on one processor, one part can run on another processor, and you're using a processor.
Oh yeah. There's So the question is, can Snort use multiple processors? Since we're splitting it into multiple processes, can you use multiple processors, or can you tie these processes to the specific CPUs in the system? You can do that with things like, you can force CPU affinity or process affinity on a lot of operating systems with their. They have native tools to do that, so you can force the process onto a CPU.
Maybe.
Yeah, maybe. Other questions? Yes?
So Barnyard is going to be available in approximately 2 weeks. When is Snort 2.0 going to be available?
So the question is, when is Snort 2.0 going to be available? Well, gee.
Preschool.
Yeah, when the kid goes to preschool. Now, luckily my wife is a morning person and I'm a night owl, so we'll have pretty good coverage on the kid for about 20 hours a day without any problem. But the big problem is that between the new company and between the new baby, my time is scarce. So I'm projecting that it's going to take 3 to 6 months to get Snort 2.0 together. My release schedules are notoriously optimistic, though, so I wouldn't bet on it being done before the end of the year. But there's a possibility. It's open source, so if you want to contribute, I love contributions. Any other questions? Yep.
You were talking about setting up Snort 2.0 for doing unified logging I'm assuming this file. Is there any plans on doing it to say like a socket or some other device so that you can say like distributed ideas?
Yeah, okay. So the question is, with the unified logging, it spools to the disk right now. Is there any planned option to get it to log to a socket? The way that we're actually thinking about implementing this is have Barnyard write to the socket. Write a Barnyard output plugin so it reads the spool files and spools the data out over the network instead of reformatting it for local storage. Just send it out over a socket so you can do distributed IDS with it. Yeah, that's exactly the way we're headed with it. Other questions? Yep.
You mentioned earlier that you plan on Snort integration with firewalls and also host-based IDS.
Well, the firewall integration. Okay, so the question is, when's the host base going to be out? When's the gateway IDS going to be out? Yeah, gateway IDS is out right now. You can actually go out on the net and get that. It's not based on 2.0. The host base system is purely based on 2.0, so you have to wait for Snort 2.0 to come out before you'll be able to do that. And there's no guarantee that we're actually going to pull it off. I think we are. I think we've got the architecture planned out properly. It's just a matter of actually getting a chance to sit down and implement it. Anybody else? How are we doing on time anyway? I'm out? Okay. Well, good enough then. Well, thanks for coming, everybody.